In this video, we're going to be discussing the basic sort of way that electrons are arranged in an atom. So this is the currently accepted model of the atom that is based on quantum mechanics. And sort of the foundational idea behind our understanding of electronic structure within an atom is that the energy of an electron is what dictates where it's likely to be found. And I'm going to start using this abbreviation for electron, E-, pretty commonly. It's a pretty standard abbreviation. So if you see E-, just means electron, a little bit of a shorthand. But since we're going to be talking a lot about electrons, it will come in handy for both you and me. So the energy of an electron in an atom dictates where it is likely to be found. The location of an electron is described by a mathematical function. This function is known as the wave function. And essentially what the wave function gives us is a probability distribution. It produces a probability cloud. That we call an orbital. So the orbital is just the region around the nucleus where a particular electron is most likely to be found, or where an electron of a particular energy. So at any given moment in time, we cannot know exactly where an electron is, but we can know where it's likely to be. We can know that it's almost certainly within this particular region of space that is outlined by our wave function. So we cannot know the exact position of our electron. This idea that we cannot know exactly where our electron is known as Hessenbergs' uncertainty principle. Which essentially says that the more precisely we know the momentum, aka the speed at which a particle is traveling, the less precisely we can know its position. And vice versa, of course, is also true. So there's sort of this inverse relationship between how precisely we can identify how fast an electron is moving with where it is in space. So if we're able to use the wave function to kind of narrow down that our electron is likely within this range, or likely within this area, rather, that's also giving us kind of a range of speeds at which it is traveling. But we cannot know precisely both at the same time. If we know the momentum precisely, the electron could be anywhere in the universe. if we know the exact location of an electron, it could be traveling at literally any speed. So the main idea to take away so far is that electrons are found in orbitals, and orbitals are just regions of space. So orbitals come in four main flavors, so to speak. Four main shapes is really the big difference between them. So they are known as S, P, D, and F orbitals. So S orbitals are essentially spheres, or not essentially, they are literally spheres. So that's sort of the most straightforward of the shapes. P orbitals are sometimes referred to as a dumbbell shape because they have sort of this narrow point in the middle and flare outwards towards the end. So note that I didn't connect those two lobes, is usually what they're referred to as. That there is actually a plane that goes through here where the electron cannot be. This area is known as a node. Is just any place where the electron is not allowed to exist. That the physics says no, the electron cannot be right there. Note also that the nucleus is in the center of all of these diagrams. I choose generally not to draw it in because especially in the orbitals with nodes, it gets a little bit confusing if it looks like there's something there, but the electron cannot be there, but the nucleus would be right at the center of my s orbital, and the nucleus would lie on this node. So the nucleus is on this plane in between these two lobes, but the electrons cannot be anywhere on that plane if they exist in this p orbital. So they can be up here, the electrons can be up here, the electrons can be down here. The electrons can travel from one place to the other, but they can't ever be on this plane. Next up, we have the d orbital, which adds a second node. So essentially we're adding a node every time we move up in shape. Phrase doesn't really make sense, but it's fine. So the d orbital kind of, if we took our sphere and we cut it in half horizontally to make our p orbital, now if we take that sort of dumbbell and we chop it in half vertically, what we end up with is a kind of four-leaf clover shape. So we're adding another plane where our electrons are not allowed to be, and we now end up with four lobes that kind of point towards the corners of a square. We have a plane running vertically and a plane running horizontally. Where our electrons are not allowed. And then last but not least, we have the f orbitals, which are complicated, to put it simply. So the shape is not one that's easy to draw, but what you want to imagine, and we'll look at a 3D model of this in class. What you want to imagine is taking that four-leaf clover shape, where each of those you can kind of think of the lobes as looking like a balloon, more or less. Take that four-leaf clover shape from the D and slice it right in the plane of your screen so that you're splitting it, the front away from the back. So you kind of end up with like an 8-leaf clover situation. F orbitals actually come in a few different shapes, but I think the easiest one to think about is sort of that 8-leaf clover, so to speak. So we end up with, I'm going to attempt to draw it, it's going to go poorly, with sort of four lobes that point towards the front, and then four lobes that point towards the back. I am not good at art. So we have 8 lobes that would be pointing towards the corners of a cube, if that helps you visualize it. So I won't ever ask you to draw an F orbital, but they're complicated, is the gist of it. So orbitals are kind of the most fundamental organization for electrons, but we also have some larger groupings. So orbitals get grouped into what are known as subshells. And then subshells are grouped together in shells, into shells, sorry. So the subshell is a set of orbitals of similar shape. And the number of orbitals in a subshell depends on which shape we're talking about. But it is always the same for a particular shape. So any S subshell is just one orbital. So an S orbital and an S subshell are really the same thing. They don't actually get grouped into multiples. But a P subshell always contains 3 p orbitals. So p orbitals kind of always come in threes, and the way that they differ is different orientations. So essentially you would have your dumbbell shapes aligned along the x, y, and z axes would be your 3 different p orbitals that would all be identical in size and shape, just oriented differently in space. The D subshell will always contain 5 orbitals, again oriented differently. Grab that for right now. And then the F subshell always contains 7. So it's all odd numbers, 1, 3, 5, 7, going with increasing numbers of nodes from the simplest shape to the most complex shape. Then the shell groups subshells, is also known as the energy level, or sometimes the N level. So these are a group of subshells of similar size and energy. Which subshells are present depends on which shell you're in. So in the first shell, often referred to as the n equals 1, the only thing that you have is an S subshell. There's nothing else there. and this is referred to as the 1s subshell. So when we're referring to a subshell, we list the energy level, the shell number, and then the orbital shape is how we identify a subshell. So in the first shell, the 1s is the only thing that we have. We should note also that this is the lowest energy shell, where the electrons are closest to the nucleus, meaning we have the smallest orbitals. So from here, we're moving up in energy. The n equals 1 is the lowest, and then the n equals 2, and then the n equals 3, so on and so forth. So in the n equals 2, or the second shell, we add a subshell. We have the S, we also have the P. So the S and P subshells are both present. So we would have, more specifically, we would refer to these as the 2s and the 2p subshells. When we move up to the n equals 3, we add our third shape. We'll have SP and D subshells all present that we refer to as the 3s, the 3p, and the 3d, respectively. And then at n equals 4, we have all of them. SP, D, and F subshells are finally all present. As the 4s, 4p, 4d, and 4f specifically. So n equals 5 through 7 are the only ones that are going to get used. Also all contain SPD and F as well. So after 4, everything else stays the same. So within a shell, the energy of the subshells increases with the number of nodes present in the shape. So that means that S is always less than P, is always less than D, is always less than F within a given shell. So for instance, if we're in the n equals 4, 4S is less than 4P, is less than 4D, is less than 4F. Within a subshell, the energy of all orbitals are equal. This is what we call degenerate, when things are equal in energy. So if we want to kind of represent this organization structure visually, I'm going to go down to the next page here. Yes, I still have it. We want to represent this visually. We get a structure that kind of looks something like this. So looking at our different shells, we've got the n equals 1 down here, which is just our 1s orbital. Our n equals 2 encompasses the 2s and the 2p. The n equals 3 encompasses the 3s, 3p, and 3d. And then the n equals 4 has, let's make my highlighter bigger, this will get easier. has the 4p, 4s, 4p, 4d, and 4f. And you will notice that the shells do not go strictly in energy order. So there's some overlap in between, say, the n equals 3 and the n equals 4 here, that this 4s subshell is actually a little bit lower in energy than this 3d. So it's not a super straightforward energy order of like everything in the n equals 3 is lower. There can be overlap between subshells. So it's important to remember that within a shell, S is always lower than P, is always lower than D, is always lower than F. But we can get sort of some crisscross between shells. So how do electrons actually kind of fill this situation up? There are a few rules that are generally followed. So when electrons are added to an atom, we think about kind of building an atom from scratch and putting all of the electrons in one by one. We generally fill orbitals according to certain rules. So there are 3 rules. The first one is known as the Aufbau principle. It says that electrons will generally occupy the lowest energy orbital available. So we always kind of start from the bottom and work our way up. The second one is known as the Pauli exclusion principle. It tells us that each orbital can hold a maximum of 2 electrons. And that when 2 electrons occupy the same orbital, they must have opposite spin. So electrons have a property known as spin. It is not that the electrons are literally spinning around like little tops. It is a property related to magnetism. So any particle or any object that has both charge and spin is magnetic. So electrons are tiny magnets. They are negatively charged and they have the property of spin, which means that they are tiny little magnets. So for electrons, we generally refer to the spin as either up or down. Sometimes you'll see this referred to as plus 1/2 or minus 1/2, but up or down is the more common. The plus 1/2, minus 1/2 is a little bit more specific because there are different kinds of spin that a particle can have. Just be aware that there are 2 different spin states that an electron can have. And because we often refer to them as up or down, we typically represent electrons as arrows pointing up or pointing down to show the different spin. So we represent these as up or down. And then the third and final rule is Hund's rule, that tells us When orbitals are degenerate or equal in energy, you will place one electron in each orbital before you pair them up. And that all unpaired electrons must have the same spin. Doesn't matter if they're all up or all down. But they just all have to match. So if we go to apply this and try to figure out how the electrons are actually organized in an atom. Let's do vanadium. First thing we want to be aware of is how many electrons are in our atom. For the moment, we are dealing only with neutral atoms. So if you look up the atomic number on the periodic table, the atomic number is the number of protons. In a neutral atom, you will have an equal number of electrons. Vanadium is atomic number 23, so a neutral atom of vanadium will have 23 electrons. So if we want to fill up this diagram, we will always start at the bottom. The y-axis here is energy, so the lowest energy orbitals are found at the bottom, and then we'll work our way up. So placing our first electron, note that you can either use sort of a whole arrow or a half arrow situation. Either one is fine. I usually use half arrows just because they're a little faster to draw, but either one is totally acceptable. Placing our first electron goes in the lowest orbital, according to the Aufbau principle. The Pauli exclusion principle tells us that we can put another electron in here as long as it points the other way, as long as it has the opposite spin. But now this orbital is full. So the Aufbau principle is telling me, okay, my next available one, or my next electron, is going to go in the next highest energy. So I work my way up. I can put 2 electrons of opposite spin in here. When I get to the 2p, I'm going to put 1 in each before I go back and pair them up. At this point, I've got 10 electrons so far. Moving onwards, I'll do the same thing in the 3s. I'll do the same thing in the 3p, filling those all the way up. I now have 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So I need 5 more. So the next highest one in energy, if we look, is the 4s. So I'm not done filling the third shell, but that's okay. I want to go in order of subshells, in order of energy. So my next 2 electrons go into the 4s. I have 3 left to place, and the next highest energy is the 3d. So my last 3 electrons go into the 3d orbital, and they're going to be spread out in separate orbitals. Sorry, 3d subshell, and they're going to be spread out in separate orbitals, all pointing in the same direction. So either all 3 pointing up or all 3 pointing down, as that is part of Hund's rule. So let's do one more example. And why don't you pause here for a moment and try to figure out the fill in the diagram for strontium. So if we look up strontium on the periodic table, we'll find that it is element number 38. So it should have 38 electrons in a neutral atom. It's just a bigger. So we're going to start from the bottom and work our way up. We can put 2 electrons in the 1s, 2 in the 2s. The next 6 go in the 2p, then 2 in the 3s, 6 in the 3p. We're going to fill up the 4s, and at this point we are at 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. The next 10 electrons go in the 3D. The next 6 electrons go in the 4p. And at this point, I should be up to 36. And my last 2 go into the 5s. So that is our filled diagram for a strontium atom.